Hi guys, we need to make this part. This had 4 tabs that broken off. This is also broken off, but I just super glued it in place to show you how it looks. And the 4 tabs drive this gear, and this gear spins here. It has something to do with oil. I don't know exactly what it does. If this is an oil pump or drives an oil pump or something with oil in an automatic gearbox from a forklift. It is a pretty precise part. It is pretty precise made. The outer diameter is like minus a couple of microns, like under nominal with like 2 microns. So like 1/10 for Imperial guys. The interior diameter is bearing fit, but is plus 0.01 millimeter. That is like 4/10 sliding fit for bearing, snap ring, an o-ring ring. Here I don't know exactly what goes in this channel. This is also pretty precise diameter. I don't remember now if this is a press fit or a couple of microns sliding fit. Probably also axially we need to be pretty precise because this part will probably stack up in something, and we don't want to influence with our height difference. So pretty precise part overall. So the material for this part is 39 nickel chrome molybdenum 3 with the commercial heat treat, but we don't care now about the heat treatment because I will send the part out for plasma nitriding. We will plasma nitride this part to have an outer shell very tough, like 60 Rockwell C, with a depth of 0.1 millimeter, like 3 or 4 thousandths of an inch, and the inner core to remain soft so it can handle the load better and not break off. At least this is what we hope. If not, the most important question when something came into the shop and it's broken, why did it break? It has an overload situation, it has a normal usage situation, it has a tiredness of material. For example, this material, if it had constant load for 30 years, the material can be just tired about the constant load and break off. I hope that in this situation is an overload situation. Basically, that means that it had a debris or metal stick between the gear and the housing, or between 2 gears, or a bearing seized up somewhere in the cinematics of this gearbox, and that was an overload to break these 4 tabs. That is what I'm hoping for. If it will break again, then we need to re-engineer the part. We probably will make another gear, and we will make with bigger tabs. We can do here like 1 millimeters per side, a bigger tab, and that will make this tab stronger with like at least 25%, because the tab is like 3 millimeters now. If you do it like 4 millimeters, then automatically we increase with 25%, and it probably work better, and we don't destroy the gear, and the gear will not break if we make this part like 1 millimeters per side, the slots larger. I hope it makes sense for you what I'm saying. 90% of my work is re-engineering part, and people don't get it. Just because it was factory made and original doesn't mean that it's better than a small shop re-engineering the part. For us to make, for example, a 30 millimeter shaft. Okay, the factory makes 30 millimeter shaft like 300 millimeter long. If they would make the shaft 40 millimeters, it will be cost like $1 more per material, let's say approximately. Then multiply that by a million shafts that they make per year, that is $1 million. So they cost the pretty expensive cost, and they reduce the cost by chance, if you understand what I mean. If they can put a smaller shaft, 100% they will put a smaller shaft, and it will hold up okay-ish. This part hold up. Probably the forklift is not brand spanking new. It had a couple of years. It is out of warranty, so the part theoretically, by design point of the factory that designed this part, it was a success because it ran out of warranty and the forklift worked. But what I do is re-engineering the part, and in many situations I put a bigger shaft. For example, if a shaft broke and you never have a breakage again in that part. But that is not cheap. For example, if you want, maybe you need to bore out in something to make room for a bigger shaft. You need to put bigger bearing. If you put a bigger inside diameter bearing, you need to put also outer diameter bearing to be larger. So you need to over bore the housing. So it is pretty complicated, but if you have like 30 or 20 machines that work 24/7 and you break shafts like once per mount, it is not cost effective to have downtime the machine one day, to have at least two people work on the part 8 hours a day to replace a skinny shaft because it was a poor design. It was a good design because it made out of warranty, but after that you need many times you need to over make and re-engineer the part to make them bigger, because in my shop, if I made a 30 millimeter shaft or a 40 millimeter shaft, basically the shaft cost the same. We don't save, my saving us €1 per material, it is nothing. But if you do a million parts, €1,000,000, it's a lot of money. Okay. And this is how the part turned out. It is intolerance. This is like plus a couple of microns. It is less than the original part. This is a minus a couple of microns. This discoloration basically is just when I hold it in the 3-jaw chuck for drilling. It doesn't affect anything. After plasma nitriding, I will put it back in the lathe and just with the Scotch-Brite polish the bearing surfaces. Basically this surface in the inner surface, and this face. Let's see how I made this part. I have a couple of clips. Bye. Okay, so the video is speed up 10 times. All the video footage that is speed up is 10 times. And now I just face the part, drill it out, nothing really special. That is a central drill. After that I drill the first clearance drill. It's like a 40 millimeters drill that I have set up for another job. After that I will drill in with a 45 millimeter drill, because the bore, the smallest bore on this part is 49 or 48 millimeters. I don't remember now. This is a 45 millimeter just to rough it out. It's very important to do the drilling first because the part moves around in the chuck, especially in a 3-jaw chuck. In a scroll chuck, the part will move when you put a really big hole. So it's always important to do the roughing first, and after that the finishing. Now I rough where the bearing fits in this part. That is the first operation, the first setup. Rough it out, finish it. For measuring, I will use a 3-pointed interior micrometer. That is the best way to measure a fit, in my experience, is the best way for far. I have like bore gauges, but the 3-point mic is the best, in my opinion. The part will have basically three setups. This is the first setup. It is roughing and finishing, the first part of this part. After that, I flip, I rough the other part, and after that, I will rechuck the part, re-indicate the part, and machine the final precision after the roughing was done and after I re-indicate the part, because in the 3-jaw chuck parts can move. I use this 3-jaw chuck quite a lot because I made an adaptive backplate with the set-through type, and it works very nicely, this chuck. I like this chuck a lot. I consider myself a 4-jaw chuck, an independent 4-jaw chuck, but I use this chuck quite a lot. For measuring outside diameter, I use a digital micrometer. I like digital micrometers better than vernier mics. For me, just making sure every time that you measure a gauge and you know that it's on size, it basically removes the operator error, because the digital mics read directly. For example, you have a 19 millimeters and you know that it's 19 millimeters, and it's not like 89 and a half because you missed a line or something like that. It happened to me before this, missing the lines, reading on the mics. I don't want to make mistakes again, so the digital mic is the way to go for me. This is why also why I use digital calipers. You can zero them out where you want it. Very simple to use, very repeatable if you know to use them. The mics depends. The vernier mics depends who basically service the mic. Others are more confusing because if you read the zero, it is a little bit past the line. Other is a little bit before the line, so it can be a little bit tricky. So this is basically the second setup. Dial it in, roughly dial it in. Now I do a facing. I put a live center to support it while I rough this end out. It is a bullnose center. I just measure it and rough it out. After roughing, I will rechuck the part and re-indicate it in on both axes, because now I'm just bumping up against the jaws, and I don't like to do this because debris can go between the jaws, or the jaws can be a little bit off. I machine my jaws always, but seems that every time they are a little bit off. I don't know exactly why. So for me to be sure that the part is straight, you need to indicate it in. Now I do a semi-finishing cut for the roughing the face down to dimensions. And this is what I told you about the third setup, the final setup. It is run pretty damn good. The face runs in like 0.02 millimeters. I think that just the surface roughness, because I indicated in how I could, the better I could, but still the indicator moves. But it's not like it's a high spot. It just moves, jumps around probably just the roughness of the turned part. After finishing the part, I move to the mill. If you notice, I have a small jack because I indicated the part in also that flange to be with the spindle in line. So I need to put like 2 jacks and move the part a little bit up to be zero with the spindle. Because you have the chuck and the chuck includes error, the table maybe has some errors or some dings, and this is the way to go. After roughing, I noticed that the part was moving a little bit, and I stopped and re-indicated the part in and finished the part. Now I saw that the part moved a little bit, removed the finishing tool and re-indicated the part in, and now I do the finishing. This is why it is always important to do roughing and finishing in the 2 different setups, because you will mess up. But if the part is not that accurate, you don't need to do this. This is how the old part looks. This is how the new part looks after turning. It looks pretty damn good. And it's a week later. I have received the parts back from Plasma Night Riding, and I use a Scotch-Brite wheel to polish a little bit the surfaces, because the Plasma Night Riding makes a matte gray finish, and they polish pretty easily. It's a worn Scotch-Brite, the gray Scotch-Brite, but the gray with the large grains, not the fine gray Scotch-Brite. I use that for a lot of polishing. And this is how it looks after polishing. It looks pretty nice. This is the job done.